Hello and welcome to another exciting chemistry session. This is your host, Mr. Monsa, a chemistry tutor. So today we're beginning a new series on the atomic structure, and we're going to run a series of the atomic structure, looking at the different components that exist in this particular topic. To start with, as usual, we have to look at the learning objectives for today's session. So by the close of this session, we are required to describe what an atom is and basically its composition in terms of the structure. We have to describe the relative charges, which are just the characteristics of the fundamental particles which are found in the atom. And then we have to understand what are protons, what are nucleons, and how to determine the proton, the electron, and the neutron number. So without wasting much of the time, we go direct into the atomic structure. So what is an atom? It's a very, very cardinal question to answer. So what is an atom? So an atom is just the smallest particle of an element. You can just pause and think about the smallest of the small, the smallest of the small. So it's something which is basically very infinitesimally small to some extent. It feels as if it doesn't exist. It's the smallest of the small. So you can think of the smallest particle. Now the smallest of that particle you have thought about, that is basically what an atom is. So the smallest particle of an element, smallest particle of an element. And what's so special about this particle is that it takes part in a chemical reaction. So we say it's the smallest particle of an element that takes part in a chemical reaction. So that is basically what we call an atom. So there is an element. Let me just highlight a few important words. So there is an element that comes into the picture. So what is an element? What is an element? So an element is a pure substance. And this pure substance is a substance that you cannot split, be it physically or chemically. You can use any physical mean, you can use any chemical mean, but you cannot split this particular element. So you can get a hammer and hit on the element. You cannot split. It's just intact. You can take this element, subject it to different chemical conditions, different chemical reactions. You cannot split. You cannot split it. It's just intact. So an element is just a substance that you cannot split by either using any physical or chemical mean. And what is so special about this element when it comes to its composition, it comprises of just one atom. It comprises of one type of an atom. We'll look at the examples down below. So it comprises of one atom, and these atoms are of the same shape and same size. But the key thing is it comprises of one type of an atom. There's only one type of an atom that is found in the inside of an element. So it's a pure substance. So we have structures of an element. We just want to look at the bigger picture of an element. So I can give an example of a classroom. A classroom is an example. You just pick a room. A classroom is an example of an element. So when you open that door of a classroom and you enter inside of a classroom, what you're going to find in the inside of a classroom are pupils. But in this analogy, the pupils represent an atom. And those pupils should be wearing the same uniform. They should be of the same they should come from the same school. So for instance, your school, you go to your class, yeah, wearing the same uniform, the same color, everything is the same, it's uniform. You open the door, that is, you enter inside. What you find inside are the atoms. So basically, that is the analogy that we should have. So an element is just something that you cannot split by either physical or chemical means. When you open the element, you go inside, you enter the inside of an element, you find things we call atoms. And those are the atoms that are responsible for chemical reactions. So what we have here are just examples of elements. So we're looking at hydrogen. We're looking at hydrogen. Let me use a different color. So we're looking at hydrogen. So hydrogen element, when you open the inside of the hydrogen element, you find the hydrogen's atoms. So those are the hydrogen's atoms inside the hydrogen element. You open the oxygen element. You open the oxygen element, you find inside you have the oxygen atoms. You go to the copper, the famous copper element. When you see the copper rod or the copper sheet or the copper plate, what is found in the inside of that copper sheet are just called copper atoms. So an atom is the smallest particle of an element. We cannot see it with our visible eyes, but it exists. It's very, very small, smallest of the small. So basically, that is the understanding of this particular atom. Now, the interesting part is, in as much as this atom is very small, it comes with certain particles inside. So you can imagine the smallest of the small again contains something in the inside of it. So this is what we're going to look at in the next slide. So we're going to look at the structure of an atom. So we're thinking about something which is very small, but interestingly, in the inside of this smallest of the small, there is something contained in, that is in the inside. So the atom comes with a structure. So an atom is divided into two parts. In as much as it is very small, it is divided into two parts. So the two parts of an atom, we have a nucleus, we have a nucleus, and we have the shells. The nucleus is found at the center. The central part of an atom is made up of a nucleus. And then the peripheral, the outside of it, is made up of shells, or in other books they call them energy levels or orbitals. So at our level, we understand them as shells. So the outside of an atom is made up of shells. So when we look at this atom, we have the nucleus at the center, and then it is surrounded by, I might not be accurate on the drawings, but surrounded by the shells. So what we have at the center, let me just color it. So what we have at the center is called the nucleus, here, and then surrounding the nucleus, we have what we call shells. We have what we call shells. So basically, that is the structure of an atom. Now, we're going to talk about the three fundamental particles that are found, that is in the nucleus and in the shells. So you find something, when you open the nucleus, you're going to find something in the inside of the nucleus. Again, when you enter inside the shells, you're going to see something moving inside of shells. So remember, we started with the element. You open the element, you find the atoms. You open the atoms, you find the nucleus and the shells. You open the nucleus, there are certain particles that you're going to find. You open the shells, there are certain particles that you're going to find. And those are called the three fundamental particles of an atom. So the three fundamental particles of an atom, we have what is known as a proton, we have what is known as electrons, we have what is known as neutrons. So using the acronyms, I normally use these acronyms as pen, just for you to remember quickly. Pen. So the P is for the proton, the E is for the electrons, and the N is for the neutron. So this one takes us direct into the characteristics of these fundamental particles. So how do you characterize? How do you know that this is a proton? How do you know that this is an electron? And how do you know that this is a proton? So, this is a neutron. So a proton has a mass of 1. A proton has a mass of 1. It is positively charged by nature, and it is found in the nucleus. So remember, the nucleus is the center, and then you have the shells around. So you find the P inside the nucleus. So this is our nucleus. This is our nucleus. Okay, so that is where you find the P. That is a proton. Electrons have a mass of 1 divided by 1840. 1 divided by 1840. This is a very infinitesimally small mass, almost negligible, but it exists. So it has got a weight. It has got a weight. That is the weight of the electron. By nature, it is negatively charged. So it is the opposite of a proton. It is negatively charged. What do you find it? You find it in the shells. How do we represent? I'm sure you have seen some of these structures from somewhere in the books. So we use crosses to represent electrons. Sometimes we use dots. Sometimes we just use dots. So these will be orbiting, they will be moving around the shell. So when you open the shell, you find electrons. When you open the nucleus, you find protons. What else can you find in the nucleus? Let's go to the third fundamental particle, which is neutrons. So the neutrons have the same mass as the protons, which is 1. What about their charge? A neutron is just neutral or 0. It doesn't have a charge. So naturally it's neutral. Where do you find it? So you find it inside the nucleus, meaning that in the nucleus you find 2 particles. You find the proton and you find the neutron. Then what is orbiting, what is moving around the nucleus? That is where you find electrons. So those are the 3 fundamental particles: protons, electrons, neutrons. Protons and neutrons are found in the nucleus. Then we see electrons moving around in the shells. I hope that is very clear and very basic. So the mass of, allow me to talk about the mass of an atom. The mass of an atom is found at the central part. The mass of an atom is found at the central part of an atom, meaning what makes the mass of an atom, is the addition of the proton and the neutron. So very soon we're going to look at the mass number or the nuclear number, see how we calculate the proton number, the neutron number, and the electron number. So the mass of an atom is centrally found uh, uh, within the nucleus. So the addition of the proton and the neutron is what gives us the mass. It's what gives us the weight of an atom. So that is basically on the three fundamental particles and their characteristics. From there, we proceed and look at what is known as the Nuclide notation. What is known as the Nuclide notation. So a Nuclide notation is just a symbol. We use a representative of letter X. So the X that you're seeing here is what is known as, and its composition, which is the RAM and the RAN, is what is known as the Nuclide notation. This is a very important notation. It gives us the information about what is contained in an atom. It tells us the number of protons that you can find, the number of electrons that you can find, the number of neutrons that you can find in a particular atom. So a nuclide comes with a key. So we have a key on the right side of this symbol. So the key, on top of the key, we have what we call the RAM. RAM, using the acronyms RAM. The RAM means the relative atomic mass. The relative atomic mass. The same RAM can also be called the mass number. Remember, I talked about the mass in the previous slide. What makes the mass of an atom? The proton and the neutron. So the relative atomic mass is also known as the mass number. It is also known as a nucleon number. Remember those three names: relative atomic mass, mass number, or nucleon number. So when you go, we're going to, very soon we're going to look at the periodic table. So when you go on the periodic table, you're going to find a symbol like this, Mg with a 24 on top. So this is a Nuclide notation. So we're going to use the information that we are currently discussing to help us understanding the meaning of those numbers when we go on the periodic table. So the number that you see on top, of this element, which is a 24, means that is the mass number of that particular atom. So it's the mass number, it's a nucleon number, it's the relative atomic mass. Then we have another one here, which is the RAN. The RAN is the relative atomic number. Which is commonly known as the proton number. So back to the Nuclide notation that I gave here for Mg24 on top, you're going to find a number of 12 at the bottom. So the meaning of that number is it's called the proton number. And then what we have on top can be referred by those three names: relative atomic mass, mass number, or nucleon number. What is found at the bottom is the relative atomic number, or commonly called the proton number. Let's go and look at the periodic table. So that we get acquainted with these Nuclide notations. Allow me to clear the drawings. So we have a periodic table showing us the different nuclide notations. So we have hydrogen, we have helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium. So in my examples, I was given the nuclide notation of this 24 on top and 12 down, that is magnesium. Then we have aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. So at our level, we're only going to limit ourselves to the first 20 atoms. We'll restrict ourselves just to the first 20 uh, atoms. So I want us to determine the proton number, the electron number, and the neutron number in these atoms. So what is the requirement here? What is it that we're supposed to know? First, you're supposed to identify the atomic symbol. So for instance, I mentioned sodium atom. Your job is to go on the periodic table and locate the symbol for sodium atom. So you will find sodium atom here, that is Na. And then you find the number on top, you find the number at the bottom, then you begin to determine the proton numbers, the electron number, and the neutron number. So that is our next task. So interpretation of the nuclide. This is basically what is happening here. So when you look at magnesium, 24 on top, 12 down there, a 24 means it's a mass number, or the nucleon number, or the relative atomic mass, and the 12 down there is the proton number, or the relative atomic number. So you have a very simple exercise right there. Can you identify, or can you write the nuclide notation for the following atoms? So aluminium. So go on the periodic table and search for aluminium. See if you're able to get the nuclide. So I can help you with the first one, and then the rest you can do them yourselves. So aluminium. When you go on the periodic table, you'll find capital A, small letter L, then you have 27 up there and 13 down there. So that is aluminium atom. Let me just make a quick emphasis on these atomic symbols. So atomic symbols, they are derived from a Latin language. So chemistry is a language. So you don't have any rights to change the symbols. You don't have any rights to change the symbol. If the capital, if the starting letter is a capital and followed by a small letter, that is how it's supposed to be presented all the time. So the same way atoms are represented, or nuclide notations are represented on the periodic table, is the same way that we should represent them as well. You don't make any changes. If it's capital, small, you represent it the way it is. If it's a single capital letter, you represent it the way it is. We don't have any rights to make any changes. I needed to make that emphasis because most times we tend to become fancy with the handwriting, and we write the letters in our own way. So we don't change the letters. We represent the symbols the way they are represented on the periodic table. Right. So we have that exercise. We can write for silver, barium, fluorine, and sodium. So just to get familiar with these nuclide notations. To proceed, allow me to look at okay, allow me to look at the next slide. So here we are required now to determine is just to find. Can you tell us, as a scientist, as a chemist, can you tell us the number of protons, the number of electrons, the number of neutrons that you find in oxygen, in beryllium, in boron, in silver, in manganese, in vanadium, in rhodium, in cesium? So it's our responsibility to know these numbers, because they are very important numbers that will help us interpret a lot of things and give conclusions which are reasonable and validated conclusions. So these are very important numbers that we need to know. So when I look at oxygen, how many protons are there? How many electrons are there? How many neutrons are there? That is basically our next task. So the key thing to remember before we even start the calculations is emphasized in this comment. So an atom is neutral. An atom is neutral. An atom is neutral. What do they mean when they say an atom is neutral? So an atom is neutral because the proton number, which is the P, is equal to the electron number. So in short, I say the P is equal to the E. The P is equal to the E. So the proton numbers are always equal to the electron numbers in an atom. So when you find that the proton number of oxygen is 8, even its electron numbers should be 8. So the P and the E are always equal where? In an atom. And that is why an atom is neutral. Remember on the characteristics, the proton is positively charged, the electron is negatively charged. So the P is equal. So imagine if you have a positive 5 and you have a negative 5, when you add those two, you get a 0. And this 0 is why they say an atom is what? It's neutral. It doesn't have any charges, because the charges, they cancel each other. They are equal. Positive 5, negative 5. Positive 6, negative 6. Positive 10, negative 10. And they cancel. That is why we say an atom is neutral. This is a very important comment that we need to take note of. So an atom is neutral because the proton number is equal to the electron number. So straight into an example, we have magnesium. Can you find the number of protons, the number of electrons, the number of neutrons in magnesium? Using the Nuclide notation. Remember the X, the A, and the B, where we said this is the mass number, and this is the proton number. So we already have the proton number. The P is already known. What is found at the bottom is called the proton number. So the proton number for magnesium automatically is 12. Then you go back to the statement which is highlighted here, where they say the P is equal to the E. So if my proton number is 12, what do you think my electron number will be? So my electron number will also be 12, and that is where the 12 is coming from. So from the P, E, N, what is missing is just the neutron. We have found the P, we have found the E. Our interest is now finding the neutron number. How do we find the neutron number? how do we find the neutron number? So to find the neutron number, we use the mass number. It is stated here clearly. To find the neutron number, we use the mass number. What is the mass number? What you find on top. Remember, what you find on top of a nuclide notation is known as the mass number. So you're using what is on top and you're subtracting what is at the bottom. So for magnesium, you're using 24, which is on top, and you're subtracting what is down below, which is a 12, and you get a 12. Therefore, in a magnesium, you have proton numbers 12, electron numbers 12, and neutron numbers 12. So basically, that is how we determine the neutron number. So to find the neutron number, you just get what is on top, you subtract what is at the bottom, then you get the neutron number. Let's look at more examples just to consolidate on the concept. Okay, so we have the following examples. We have potassium, we have sodium, we have fluorine, we have lithium, we have argon, we have boron, and then those are well calculated for you. But just to confirm, so when you look at potassium, when you go on the periodic table, remember we have to be very much conversant with the periodic table. So when you go on the periodic table, you find that potassium is K. What is on top is 39, then what is down below is 19. So we said what is found at the bottom is the proton number, which is 19. How do you find the electron number? The P is equal to the E. So automatically this becomes 19. How do you find the neutron number? I said you get what is on top, which is a 39, which is a 39. I have noticed there's a mistake there. A 39, this is supposed to be a 19. This is supposed to be a 19, not a 20. And then you get a 20 as the neutron number. Get a 20 as the neutron number. So that is basically how we calculate. So here it's supposed to be a 19, and then we get a 20 there. Clear? Then what about sodium? When you look at sodium, I'm looking for my functions. Okay, when you look at sodium, sodium is N, capital N, small letter A. Then you have a 23 on top, and you have 11 down there. So we said what is at the bottom is a proton number. Yes, correct. Electron number, we said the P is equal to the E, so it automatically becomes 11. Neutron number, you get what is on top, so 23 minus 11, we get 12. Fluorine is F, capital F, 19, capital F, 19, and 9 down below. So we said what is found at the bottom is the proton number. Electron number, the P is equal to the E, therefore it's also 9. How do you find the neutron number? You get 19, you subtract 9, you get 10. So basically that is how we determine the protons, the electrons, and the neutron numbers in an atom. So we have come to the end of today's lesson. Just a quick reminder, know how to define an atom, know the parts of an atom, know the particles contained in an atom, know the characteristics of those particles contained in an atom, know the nuclide notation, and then know how to find or know how to calculate the protons, the electrons, and the neutron number, bearing in mind that the proton number is equal to the electron number in an atom. So this has been Mr. Monsa, the chemistry tutor. Until next time, bye-bye.